My name is Pheely.
And I am Liam.
All right, so we are back for the second episode. Wait, this is the third
Third
episode
episode
now
already.
for Hyperthesis. Time flies. Oh, wow.
Yeah, you thought it was the second episode because you were probably editing the second one recently.
Yes, I'm pretty tired today. Got a long day.
Yeah, fair enough.
But hopefully you're ready for a bit of a longer day because we'll be talking about your research a bit later. But to start off, we'll just go around the group and see what we have learned in the past week, whether it's something new or something old but new to us. Anything interesting that's piqued your guys' interest?
I learned what diffraction spikes are. I don't know how I missed that, but anyone who does photography probably knows what these are. And so you know how the James Webb telescope is up there and doing its thing now, right? For anyone who doesn't
Sure.
know,
Yeah.
they you've probably heard of the Hubble telescope. And again, I'm no astronomer, so I don't know the details, but Hubble telescope, pretty famous telescope, took a lot of nice pictures of things in the universe. James Webb telescope is kind of like the next big one. And I say recently, it's not that recent now, but recent enough as far as physics timescales are concerned. They focused the telescope, so they lined all the mirrors so that when they get an image, it's not all blurred and messed up. And the focusing star they used, I forget what it was, but it looks like this big 6-pointed like star you put on top of a Christmas tree or something. So I was wondering, I was like, what are those? Why is there spikes on this? And I went and looked into it, and they're called diffraction spikes. They basically form because of the way light diffracts in your aperture.
Yeah. So if you do photography, like the smaller your aperture is, the more the more amount of spike you're gonna obtain, right? So if you lower your aperture by a lot, you can have like very spiky light.
Is that because you're changing the scale of your kind of where light enters the lens, or not the lens, but light enters the camera to be smaller and smaller, so it gets closer to that of light?
An aperture is a little hole, right?
Mhm.
Or it could be pretty big. And if you think of, like, I think also like dispersion, you get more dispersion the smaller the holes are, and it bounces around more. I'm not exactly sure about the ray part of it. I actually never really do any actual writing down the trajectory of the rays, where it goes, but I'm sure there are people who do that.
Well, diffraction's not really a ray thing, right? It's a wave thing.
Yeah, but it's nice to see the dispersion direction, like where it can go.
Yeah, so anyway, I thought that was cool. And it's like a pretty, like, all cameras have them. If you squint, you start to see these lines coming out of lights, and those are diffraction spikes as well, actually. So if you can also see them in the Hubble telescope images, you notice that every star has the same kind of, you can tell what kind of aperture it has depending on how many spikes are coming out of it. So for the James Webb one with that 6-pointed star, the aperture has kind of 6 edges. I don't know the details at all, but it's something to do with a hexagon. And so for the Hubble, there's 4 points. So if you look at a Hubble image, just Google Hubble photo or image or whatever, you'll see like all the stars have these kind of 4 spikes sticking out of them in the same direction, no matter what. Where in reality, if you were to look at a star, there wouldn't be these spikes. It would just be a ball.
Well, when you look at the stars, your eyes also have aperture, so you might also see spikes if if it's far enough. I mean, you can see spikes in your eyes when you look at light bulbs. So I would figure you can see spikes when you look at stars.
Yeah. I mean, maybe it shouldn't be.
Especially we have like myopia, so nearsightedness is pretty sometimes more obvious, right? Than people who have 20/20 vision.
Probably shouldn't be looking at stars with your naked eye as well. At least not, the one nearest to us.
Well, yeah, but you can look at the moon, you can look at the rest of the stars.
A cool experiment you can do just to see diffraction is if you take 2 fingers and hold it super close to your eye and just close your fingers enough that there's a very small space, you'll start seeing kind of overlapping shadows. And that is diffraction that's easily reproduced. It helps if you look at a bright light too, or some sort of bright surface.
Yeah, basically it's like a small slit, right? Like a thin slit.
Exactly. You should see just some sort of alternating darker and lighter regions that are diffraction
I
pattern.
did for fraction of a second. Okay, let me put
So
my
that's
glasses back on.
That's a fun science experiment you can do at home with the kids.
You can make a double slit experiment too with paper and a very fine carpenter knife, but that I tried to do it once and gave up after about 2 minutes. I was too impatient.
Oh, another example of diffraction. If you happen to be living in Canada, at least for Canadian money, I know, the money that we have has a circular clear window that's made of plastic. The whole money is made of plastic, for those who may not know. And if you shine a laser through that circular window onto a wall, and it's either a bright enough laser or a dark enough room, it will show the denomination of that bill. So for example, taking a $20 bill, it will literally show $20 if you shine a laser through that window. It's fascinating.
A lot of anti-counterfeit technology for money passports use like diffraction patterns like engraved into it, right? Because it's really, really difficult to replicate. Like,
should maybe
extremely
clarify like this simple example of diffraction in case someone doesn't know what it is. So like if you have a wave traveling in water, like at the beach or something, and there's a wall in the water, the wave can like hit the wall, but the waves will kind of go around the edge of it. Maybe that's a bad explanation, but I have a hard time explaining it in not a double slit experiment context or a single slit.
Well, double slit, those have a lot of interference, right? If you think of diffraction as like a bunch of waves interfere with one another.
No, I think a diffraction is if you have like a wall with a hole in it and you put a wave through it, then the wave comes out as a spherical wave on the other end, even though you send a plane wave in.
Mm-hmm.
And
I think so.
For those of you who may just be learning about this, light is both a particle and a wave. So depending on how you look at it, it can behave as a wave and so diffracts, or sometimes it can behave as a particle, such as if you look at it from a particle physics perspective. So it can be both, and that's why it diffracts.
It always confused me so much in physics that things are both particles and waves, and you kind of just choose whichever one works, because like sometimes the wave description doesn't and a particle one does, and it's like, yeah, that's kind of like, it's very fundamental, but I still don't understand why you can just pick and choose.
But diffraction is an exclusively wave phenomenon, though. Like particles don't diffract, right? But particles that appear to diffract is because they're small enough, right? That have like a is it Debye's wavelength? Yeah, in a range that the same Debye wavelength as the slit, or smaller.
Is it de Broglie or however you pronounce it? De Broglie.
De Broglie. I think de Broglie. Debye is thermodynamics.
De Broglie wavelength is just the wavelength of that matter can have and stuff like that.
Yeah, so we have de Broglie to thank for showing us that what we traditionally thought of as particles, such as electrons or protons, neutrons, did have a wavelength if they're traveling at a certain speed and they have a certain mass. Technically, the Earth has a wavelength.
Yeah, I was gonna say, I remember in grade 11 calculating the wavelength of my cat because it was a homework assignment or something like that.
Yeah, everything has a wavelength, basically.
We're on the same wavelength, bruh. Anyway, I always think it's interesting that you can kind of just pick and choose particle and wave descriptions, and sometimes one works, sometimes the other works. I don't really like that very much, honestly, but it is what it is.
Well, it's not like you pick and choose, it's how
Well,
you
kind
observe
of.
it.
Like, sometimes you can't do something with the wave description. You have to use a particle description. Sometimes it's the other way around. And I know that there's like certain regimes where one works and one doesn't. I like how this so. I really like that the introduction to most of these podcasts so far is us just trying to remember physics that we haven't thought about in years and years. We're just like, is this right? Is that wrong? I don't know.
Yeah, the names start to confuse me, the bi, the broy.
The
Oh.
broccoli,
Yeah, it's literally spelled like the broccoli.
the broy, or something like that. Anyway, we've been ranting about this a little too long, I think.
So, we are going to focus today on Pheely's research. We heard a little bit about it in the first episode, and now we're going to delve in deep, ask him some interesting questions. But to start off, Pheely, tell us a bit about what you do.
Well, I think as I have mentioned before in the first episode, I work on kind of strange, new, novel field of physics that we kind of try to come up with, which has to deal with design, architecture, and a little bit on like the nature of optimization, and basically use physics in a new way that people don't think about or think it's possible, basically. So to start, I think I'll talk a little bit on designs and why are we interested in it. So designs are abstract, and they are not something that we think of as physics, like physical things, physical phenomena, or things that you can touch, things you can, a projectile. You throw a ball. There's a physics that describe it. There are quantum mechanics that describe small things. You can do celestial mechanics to describe the galaxies and whatnot. But design is something people don't think as physical or even describable using like physics. So we're gonna do that using physics to analyze design. And what we mean by designs are something that humans create. So basically artifacts. So if you think of everything around you, you look around, hopefully you're not in nature right now. If you're taking a walk in the woods, probably not. But if you're in a building or if you're listening through your phone, everything you see that human creates has to go through design process. Either engineers, architects, and we evolve, as humanity progress, the designs became more and more and more complex. We are not just designing like a fishing rod using a stick
Yeah.
anymore. Like we are designing phones, we're designing satellites like the James Webb telescope. It's huge. Like these projects take years. Even designs for a basilica or like a huge church took hundreds of years to build and figure out. The complexity in design has grown so much, but we don't really have a way to actually deal with that complexity. So one thing we look at, well, which I will mention later, are warships. Like if you think of it, it's a big design. If you have like a World War One, World War Two battleship, like they are huge. There are hundreds and thousands of components that's connected to one another, and everything is complicated. So, but you still have to worry about, is this stable? Does everything work well? That's why it's so hard, really difficult to make these designs practical. And like the engineers have spent countless hours and money. There are ships in the U.S. Navy who are, I think it's the Sumval class that they plan to have like 34 of them. It turned out to have like at the end because over budget and over time that it came out to be like 6 of them. So there are actually a lot of issues trying to deal with complexity.
Yeah, they're massive. Like I don't know about the ones you were just talking about, but like what was the first design was probably like a sharp rock or a pointed stick by cave people back in the day, and now we're making these like city-sized aircraft carriers.
Yeah, because
Like-
they hold like almost like 5,000 people, like the bigger than some small towns.
They're insane. I've been on an aircraft carrier once, and yeah, like just feels like you're on land.
Yeah, I'm sure it's just like a full city. The deck, you have a bunch of ships, carriers, like, and they never travel alone too, right? You have auto cruisers, destroyers escorting the aircraft carriers. So you're in like literally you are like a country just moving through the ocean. So back to complexity. So the question is, I think, very important in design is how does complexity manifest in these large scale designs? And when you think about it, what can you use to analyze these? People use mathematics, like what branch of mathematics? Engineering, what branch of engineering? You have people in engineering study design, just come up with their own parameters, optimization, and whatnot. But it's not an intuitive theory. I think I talked about this before in the first episode that a lot of what we do as physicists are what I call it, on my group like to call it, the concrete abstraction. So the idea that we make an abstract concept to make something that's hard to understand concrete, like something like the word force, entropy, heat capacity. These in itself don't really mean anything. They're just some words that we have to define that somehow make our understanding like intuitive. We can understand the world better. So we do that a lot to natural phenomena, right? We try to understand thunder and lightning. We have to study quantum mechanics. We have to study electric circuits, electricity, electromagnetism. But we don't usually apply these to something that's very abstract, like design. So why not? But the problem is, the main challenge is, how do we do that? So before I get to there, let's talk about design in general. What is the problem? What is the challenge in design that like in complex design that make us right now that what we do in large scale design, we throw in some optimization algorithm, are basically a big guessing game that we use computers to help us do it. So in any physical systems, we look at arrangement problem. So the two parts, arrangement and routing. So where to put things and how to connect them. So imagine you have like a water system, like a sewage, right? A sewage system. You have to know where to put your pipes. That's routing. And if you want to know where to put your stations or your subway station, is a problem of arrangement. So those are very, very large scale. But if you think in a ship, like where to put your bridge, where to put the engine, where to put the propeller, or where to put all the bedrooms. So these are arrangement problems that people have to figure out. And I think historically, there are some people who do like a design principles or try to figure out a way to put things efficiently, and they're doing pretty well until we have to put 10,000 units of stuff down, and then when that becomes a big problem.
I think of like an old pirate ship or something, right? And they probably just, to get to that design, someone sat down and said, all right, the captain's quarters makes sense if it's here, and then they did it, and then a few months at sea, and they were like, oh crap, maybe it makes more sense to put it somewhere else because of this problem we've encountered. So it would, like, the simpler the design, the more you can just kind of figure it out through trial and error. But if you got, this 10,000 unit, like you said, battleship, you're not going to build one and be like, oops, let's swap these two around now.
Yeah, there's some phones that are made to like, oh, we can exchange interchangeable parts. You can put this here on by yourself and stuff. People do that to PC all the time. When you build a PC, you want to switch things around. But that's a very small scale. Like if you have a $1 billion battleship or a warship that you're gonna build, that a prototype would cost you $1 billion. I mean, it's gonna be tough to change things around. On the note of the word battleship too, I think I use that quite a lot, but it's not exactly correct because battleships were retired basically. They don't make battleships anymore. Battleships are what we see in World War II, right? The big guns, like the largest size warship, because they have highest firepower. The Yamato, those stuff, huge. But since the invention of cruise missiles, it just rendered those battleships ineffective. They just get sunk by one missile. So you rather just have a bunch of smaller naval ships that can carry missiles and just go shoot everybody. So that's the spirit of changing the word to warship. You have different class like cruisers, destroyers, light cruisers, whatnot. Not very important for the project. Nevertheless, I just want to clarify that. So the problem now is about design analysis. Should we analyze design when it's almost built? Then that's hard. There's a lot of things going on. So what we are interested in is early stage design. So you don't need to know how big the bed is gonna be, even how many guns are supposed to be, or how actually the size of the ship. You just have some design requirements. Something like, oh well, we have this much money. We have to put a propeller there because it's very important. You have to put engine the very, very early stage. So it's just to reduce confusion and reduce amount of data. So to understand things, like in physics, we start from simpler systems. That's what we try to do too. So we're basically going to try to use physics to understand the most basic of ship design. And how, is there something like force? Is there something like entropy? Or is there something that help us understand what it means to design something? Or how come designs come up from these
If you want to construct a
problems?
battleship, you must first invent the universe.
I was just wondering, to actually produce these designs and try and figure out, okay, here's the propeller, just from these basic, okay, it needs this many rooms, it needs this many guns and propellers and a command area. How do you actually develop those algorithms? Do you start from something simple or just kind of mash everything at once and say, here, have at it? Or does it start with, say, oh, here's a propeller, where's the best space to put this, and then build from there?
The thing is, that's not what we are trying to do. So, for example, what engineers try to do, what architects try to do, is to find solutions. What I mean by solutions are like the actual designs of things. So those people, engineers, they use like optimization algorithm, something that, well, I've just thrown keywords around, like simulated annealing, which is basically, if you know how to anneal metal, you basically raise something really hot and make it slowly cool down. It turns into some kind of solution or configuration that serve your purpose. People do like molecular dynamics or like gradient descent, which is basically what machine learning is. And so those are ways people do these now. So they just throw a bunch of requirements and elements together into this algorithm, and it spit out a solution. So as an analogy to what we do in physics, like, you know, if I throw a ball, the engineers, or they are interested in where the ball land and what contributes to making the ball land. It doesn't matter that much. If they can find where the ball land accurately, that's great for them. So a lot of designers, what they want to do is find solutions, no matter what it is. So they come up with this crazy algorithm, take a year to run, on supercomputers. But that's not what physics is about. Physics just like, we don't care that much about where the projectile is gonna land. We care how it's gonna land and why is it behave like that. So what we try to do is not finding the solution, is to find a knowledge structure of how the design problems create certain kinds of solutions.
Well, you probably do care about where it lands, but yeah, you want to know why and how so that you can predict it, kind of thing, I guess, right?
Yeah, but
Maybe.
but these systems are so large that like it's hard right now to to actually figure out, this actual solutions. But to at least have some understanding on the fundamental level, like if you know that like these type of designs are not stable, like theoretically not stable. And what I mean by not stable, not just structural, but like in terms of where things are itself, like it has some vulnerabilities that just because the layout is like that, is vulnerable. And right now, there's aren't really a great way to do that in early stage.
Do you know what structural stability sounds like? Catastrophe theory.
Well, the thing that we're gonna use to tackle these problems, because if we have a lot of design elements, basically, the little components that's connected to one another in a certain way. So that sounds familiar to us. Like it's actually like a system of particles. If you have a gas in a box, right? There's a bunch of particles that they interact through Coulomb forces. Well, what if each particle is like a design component, and instead of the Coulomb force is anything we'd like to be, like a routing cost, or like the distance that it wants to connect, or anything that we decide to be like a cost criteria. So we can use that to basically do physics on it. It sounds simple. So the field that fields that deal with those type of phenomena is called statistical mechanics. So, and also part of it is thermodynamics.
I was going to say, when I
And so
think of
these are
statistical mechanics, I kind of think of just like quantum thermodynamics, but that's maybe not quite exactly a good way to think about it.
well, you can do quantum in it, but
You don't have
I think
to.
that's it. We are looking at different scale. Well, we shouldn't.
No. But when I think of statistical mechanics, I think of like quantum thermodynamics, because that's usually the kind of context you're taught it. People teach it to you.
Yeah. To me, thermodynamics is like a subset of
Yeah.
statistical mechanics. It sounds weird, but like it's literally like the macroscopic way to look at statistical mechanics, right? Those thermodynamics, that's why they teach you first thermodynamics, the Carnot cycle, the steam engine, to basically help explain how heat and free energy and these thermodynamic terms work, and how to do calculus on it. But when you get to statistical mechanics, like Liam said, there are a lot of quantum and things that you can do that because statistics in a way has to deal with a lot of probabilities distributions, probability function sounds like quantum
Yeah, quantum
mechanics.
mechanics is just statistics, I guess.
Yeah, I mean, there's the work. My work is also based on basically how people form statistical mechanics purely through information theory. So it's basically you can derive the whole statistical ensembles through information alone, just because anything has self-information. So by that, if you know the distribution and whatnot, you can create statistical mechanics of it. That's why we believe that we can do this, because design is literally just information lying around. Nature is information lying around. We just use information theory that's applied. We just call it physics, statistical mechanics, and whatnot. But what we do in StatMech, the important part is we want to look in a macroscopic picture. Because if we look at microscopic, we look at the little parts, the little particles. Well, it doesn't tell us that much about it. That's why we choose statistical mechanics. Because when a lot of things, almost everything we do in thermodynamic quantities and stuff are summation, and they are averages. They are something that add all the effects together.
It might be worth pointing out to for not the non-physics educated community that thermodynamics and statistical mechanics and whatnot. If you want to model like the air in the room you're in, it'd be very hard to model every single atom or molecule on its own and then combine that picture. So thermodynamics is kind of like this macroscopic picture that, although you don't really care about each individual atom or molecule or whatever, you get like a macroscopic picture of what's happening, and it works really well. So yeah, exactly what you're saying. You don't want to look at each individual thing. You want to kind of look at the overall picture.
Yeah, and it's not a strange concept either. We do that all the time. We do that in electric circuits. What is drift velocity? What is EMF? What are current?
Yeah.
Electromotive force.
Current's a really good example.
Yeah, like we don't look at each individual electron, how fast it goes, but we know the current flows, and it's just like actually I think it's a mean.
Yeah.
It's an average of some kind, right? It's an RMS. I think it's a root mean square of the velocity.
Charge per unit time.
Yeah, if I remember correctly. I'm trying to remember undergraduate physics, but
we're gonna make some mistakes on here, so let us know. Let us know when we make mistakes. I've made a few of them, so people have noticed some and they haven't noticed others. So they're not big mistakes, but it's more of like small ones.
So I think I'm going to talk a bit about why thermodynamics are so useful. Like thermodynamics have been used since like this era of steam engine. Basically, they just want to figure out how to make it the most efficient. And people think like, when you hear all the time, people saying machine have 90%, 99% efficiency. Not true. Impossible. Thermodynamically impossible. Because the most efficient machine is Carnot cycle, right? The Carnot machine. That was like 70% or something. Maybe I'm wrong, but I think it's not up to 90.
I would argue that the exception to that would be where you have, technically not closed systems. So think of heat pumps or air conditioners, where they can be 500% efficient kind of thing. Not quite the same as these different Carnot cycles and everything, but still, we can have situations where things are more efficient than 100%.
What does 500% efficiency even mean? Because I thought efficiency was like if you're putting so much energy into a system, it's 100% efficient if all that energy goes into what you want it to.
I guess you are looking at more so coefficient of performance.
Well, I guess, yeah. But that's what I think of when I think of efficiency. So what does 500% efficiency mean?
that's just impossible. You put like a one
Yeah, I
juice
was gonna
in
say
and you get
like
5 juice out.
Again,
And it
there's
just
an
doesn't make
exchange that
sense.
goes on where you're able to draw, like in a heat pump, you're able to draw energy from, let's say, outside a house. So you maybe put in 1 joule, but the actual heat that's output, so the air temperature, it's heated using 5 joules kind of thing. So it's a heat exchange process that lets it be more efficient because of a difference in temperatures between two different areas.
But you have to add a lot of work into it. That's still, is well, as I don't think it's thermodynamically possible because work, first, second law of thermodynamics.
we're talking about different definitions of efficiency, I think, because like on some level you can't go above
Yeah.
100% efficiency, but I just want to call out my mom because I know she's listening to this, and that's how your new heat pump works, Mom. So, and Dad, I guess, but that's why it's so good.
Anyway,
Mhm. Well, as I think as normal people, when you hear these efficiency, like it's fine, But as physicists, I was like, that's impossible. That's just wrong.
It's like my dishwasher soap. It's called like quantum soap or something. It's like buzzwords that make people want to buy it. It worked. I bought it because it said quantum.
People try it, and they do it really well. So just go back to the thermodynamic quantities. Like, I think what people hear a lot is entropy. Like, entropy is such a neat concept. People try to define what entropy is, and some people study it all their lives, still don't really aren't really sure what entropy is. Some people say it's a measure of disorder. Some people say it's just an intrinsic thing of chaos or something. And I'm still struggling to actually define it.
I was gonna say I don't think I've ever understood entropy.
To me, it just is we quantify what we don't know about the system.
Yeah, like I know, but like at the same time, it still confuses me. But anyway, so entropy. How does this relate to your battleships or your maybe the not battleships?
Well, yeah, so these quantities in tandem, like entropy, heat capacity, free energy, so these can provide a picture of how these systems work. So what I mean by picture is literally like you can make diagrams that shows how these works. They're called phase diagrams, or you can make probability distribution to show where things want to be, not where things will be, but where things want to be, so that the system is happy. So like the laws of thermodynamics, right? They have one of the laws say the entropy always increases, the universe entropy. So in any system that wants to go to higher entropy, if you want to go to lower entropy, you have to add work into it. So if we want to find a solution that the system really likes, it means you have to find a solution with maximum entropy. And that's what people do when they do some type of optimization and whatnot. The peak parameters, they try to extremize it, either minimize it or maximize it. But in nature, thing just maximizes entropy. If you think of classical mechanics, things extremize action, right? That's why you got Lagrangian mechanics. But in macroscopic, in statistical mechanics, we extremize entropy. So if you can define entropy, it tells a lot about the system, where it wants to be and whatnot. And we have also free energy. I think when people hear the word energy, they think of something as an intrinsic ability to do something, right? Like kinetic energy, a ability to move, potential energy, the energy to actually also move, but from just being in somewhere. Well, that's my poor definition of energy, but
Yeah, well, we could be here all day talking about that.
yeah, the free energy is basically like if you say it's ability to perform work. Basically, this is me explaining a lot of stat mech, but you can have an idea of what system would look like or what configuration or what solution it would try to get into by looking at these thermodynamic quantities. So, if it has really low entropy, maybe, it's not really probable solution. That's why we don't have those solutions. Or that's why it doesn't come out of optimization algorithm. Or that's why we shouldn't use those solutions. Or we can define auto parameters. Like what I use is design freedom to say like, are these solutions have more freedom to design freedom? So are they more stable? Can solutions be robust? Can solutions be fragile? So we use these thermodynamic quantities to actually basically retranslate or rederive again for something that's intuitive. Like I said, for robustness, can design be robust? And that's kind of help to, like in large scale complex design early on, to figure out what we shouldn't look for, or what type of things we should look at, or what type of solutions are possible, what types of solutions should be called good, should be called bad. Sometimes a big problem in optimization is that you don't know it really works until you create a prototype. That's why people do CAD, the computer assisted design, right? AutoCAD and whatnot, to actually figure out like if you build a prototype, would it work? But sometimes the system is so large, it's really difficult to make a CAD. So you have to figure out, well, it doesn't work because theoretically there are some design requirements that conflict to your possible solutions that you think of. So you can basically rule out a lot of bad solutions. So what we were trying to go for is basically provide these type of understanding, what if you have these design requirements, would it lead your solution into certain trajectories?
So I'm curious, how do you put this into action? So you're talking about ruling out different designs and finding this kind of optimal parameters. But how do you decide, okay, what are we inputting into whatever we're doing? What general guidelines are we looking for the output? How many variables are we accounting for? What limits, or I guess allows you to choose these different aspects?
Yeah. So the project is like in a kind of early-ish stage too, because like we don't even look at like 10,000 units. That should be a lot. The downside of statistical mechanics is it has to sum, or it adds all possible configurations. So that's gonna make things a little more difficult when you try to actually compute things. But what we do is basically like we try to solve the arrangement problem, like try to understand the arrangement problem. So what we input in will be where things should be and how you connect them. So what we care about is actually clustering. What we find basically, where when certain units want to be together, maybe engine want to be near a bedroom, something. Why would they do that, right? And how it connects. So we try to understand that, and then you can add more and more layer complexity, right? You can have power system. That's one thing. And then you can have hydro system, which add another layer complexity, which needs to be fleshed out in the theories we worked on. But the thing is, this is like a curse of dimension all over again, that you add one more layer, there are literally 100 more things to think about instead of 10, and then you add another layer, it becomes 1,000. So we have still have to deal with this type of enlargement of complexity that's make it very, very difficult to do. But what's interesting about the result that we find is that we can find some features in these systems, these abstract designs of ships and stuff that look similar or really like analogous to conventional physics system, something like a magnetic system. What we see some symmetry breaking. Oh, that happened in ferromagnetic system. So we see these type of features like, oh, we have different phases, and can we have the kind of phase transition? Do we have a finite phase transition? Because what we are working on is nowhere near thermodynamic limit, which means a lot of particles. So you can average out really well. But we don't have that many units, but we can see these type of behaviors that like look similar to physics. So it gives us a little clue of that. We may be able to do this in physics.
I'm also curious. So I take it these actual calculations can be pretty computationally expensive. Was there work being done like this before computers were as powerful as they are now, or even widespread whatsoever? Could people do this, say, by hand to iterate through, for example, different configurations of a warship?
Well, no, I would say no. It's very, very difficult. If you think of Ising model, like the most like simple model of magnetic system, right? Is just the Hamiltonian or the energy term. Is just interaction term is just the nearest neighbor interaction. It's so simple. But when you get to 2 dimensions, it's become really difficult. Like Onsager, who solved it analytically, has his tricks, and he won a Nobel Prize for it. But still, people have still figure out how to solve it in 3D. So it becomes you have to do it using computers, do numerical approximations and whatnot. So yes, the expensive computation is a challenge, and my group, we use a lot of tricks to deal with it. The tricks that people use in all the quantum systems or machine learning, building networks of tensors to solve these things. Just a lot of math that we try to help computing these large systems, because like I said, StatMech, we deal with all possible configurations.
Yeah, well, that's interesting stuff. I'm always very interested in Navy things because my dad fixed submarine sonars growing up, so I really like the Navy stuff. So I'm interested to see where it goes for sure.
Yeah, that's a lot. There's a lot to be fleshed out still. So I don't know where it's gonna go. It could be big, or it could be nothing. That's the nature of research. I think we just like in term like in graduate level, like or above undergrad. We have a flashlight, and you walk in the dark, and you may find something, and you find something, you dig at it for 2 years. You're like, well, that doesn't work.
Yeah, even there's the Canadian Association of Physics annual conference coming up, and I'm gonna present a poster in it. And I think the abstract I submitted is about 20% accurate as to what I'm actually gonna present, because it all changed since then. I was gonna go down one route and I noticed something else, and now I'm going down that path. So it happens.
Oh, my talks abstracts
Yeah,
are
me
like
too.
super vague. You're like, well, we do this kind of this.
Yeah, I
on
try
this.
to be pretty vague.
Would you say they're pretty abstract?
Yeah, we still got some time, but we should probably start wrapping things up a bit. We wanted to mention ways to contact us and social medias and whatnot.
Yeah. So if you have any questions, especially for Pheely from this episode, we did look a lot into statistical mechanics, thermodynamics, and if you have burning questions, feel free to reach out to us through either email or Instagram. Those are the 2 ways to contact us. Our Instagram is just the Hyperthesis Podcast, and we can be contacted at hyperthesispodcast@gmail.com. Also, you can find us on more platforms this time. We are on Anchor, which is run by Spotify, as well as Google and Apple podcasts. And you can also add us to your RSS feed if you still use those, like I do. So, rounding out the night, I believe we have a nice story from Pheely.
Yeah, he's carrying this podcast.
Looking
We're just kind of here.
But we have talked about the physics of design and optimization, but I believe he's going to take us on a journey into the past of design and natural designs.
All right. So, since we touched on design, I want to look at, talk about a little bit on what we see. It's kind of weird to talk about in podcasts about, visual things. So, you have to bear with me using your imagination on this. So, I want to talk about on golden ratio. So, golden ratio is what we see in design a lot. Actually, almost all visual things people attributed to golden ratio. So, since ancient time, basically, because we can see this ratio in nature and whatnot. But contrary to the name ratio, because ratio implies, is it a rational number? You can write in fractions with integers as numerator and denominator. But golden ratio is actually an irrational number. It's 1 plus square root 5, all of them divided by 2. Like, that's irrational. It's not exactly a ratio in terms of rational. It's not a rational number. So, well, even though it's called ratio, it's a kind of weird, irrational ratio. So what we see as golden ratio is actually a lot. Like, if you go on a walk in the woods again, you can see flowers, shells, mushrooms, like come from really small things like cancer cells and little organisms to a large scales like hurricanes, galaxies, the star formations. They all seem to have this ratio between space, this shape, this curly kind of like shell shape. And we're always curious why. Like, why is that shape everywhere? So, to me, there are two things that these are my guesses. For a living organism, because we have to divide cells from 1 to 2, and from 2 to 4, so and 4 to 8 and whatnot. So, and it became this kind of sequence, which the famous mathematician Fibonacci, when we name it after him, the Fibonacci sequence, where it's go, I think just 1, 1, 2, 3, 5, 8. It's just you're just adding two previous numbers together to get the next one. So it looks kind of like cell division. So in organic matter or living organisms, it seems to be the consequence of having to do the meiosis and mitosis, basically. So that's interesting. But how about for inorganic stuff like wider galaxies and stars? But they also have to spread out from some way. And also about the distribution in space. If you have two things in space, where would most likely to be? If you have 4 things in space, where it's most likely to be? And someone in mathematics probably figured that out. But so I explained a bit about Fibonacci sequence, but how do you get golden ratio through the Fibonacci sequence? Because Fibonacci's are just rational; they are integers. So if you take the latest one in your sequence divided by the previous one, so you get an approximation to the golden ratio. Fibonacci sequence actually probably one of the best way to calculate or to approximate the golden ratio. Or you can solve a quadratic equation to get that 2. That's why it's the irrational number. So you can see golden ratio through Fibonacci sequence, or you can do it through geometry. So bear with me. Imagine a square, and if you clone a square beside it, so you get a little rectangle, but there are 2 squares. So now, since there are 2, the longer side create a new square with that side on top of it. So you're gonna have 2 now, and you keep doing that process. You're adding more square and make a bigger square, more square, bigger square, and it would just create this weird shape with have little squares plus bigger square and bigger square. And if you draw a line through each side of the one you create, it will create this curve that you probably seen hundreds, thousands of times in your life, that famous golden ratio spiral. So that you can create through that too. And these actually can be seen everywhere in art. So for example, the pyramids also have this golden ratio between the architecture of it, or Mona Lisa, or about the paintings. If you put that spiral on top as an overlay, you can see the important part, or where the artists want us to pay attention to in the like on the line of the spiral. And you think of posters, logos. If you think of Pepsi, it's like a logo's bunch of circles. But if you look at the ratio of where the circles are and how big the circle are, they actually closely follow the golden ratio. And a lot of design principles are motivated by this golden ratio. So if you ever use like Adobe Illustrator, they actually have like a tools that when you try to draw things, it connects things to the golden ratio. You can create a guideline grid that shows the golden ratio. So when you design, it's the most mathematically correct way to put things together. So if you do photography, you have heard of the rule of thirds. So when you see a grid in your photo or through your viewfinder, you want to put things where it intersects. Some grid you can change it to the golden ratio. I think it's 1 to 0.618 to 1, because that's if you basically renormalize to unity or to 1 for the golden ratio. You're gonna see that ratio too. So when you put things on these intersection on those lines, it's considered conventionally or by constructionally pretty or pleasing. And you can see these all in nature. So that is a little short story on the truth of the world, the mathematical construction of beauty.
We came full circle, or a full spiral, I guess. Started talking about diffraction spikes in photography, and then we ended up with the golden ratio in photography. So yeah, that was fun.
Very nice.
I will just add in there, as someone who studies plants now, the golden ratio is very prevalent in some types of plants, and it has to do with efficiency. I encourage you to look that up more, but it's to maximize the amount of sunlight that leaves can get, that some plants arrange themselves in such a way. But very interesting.
The design efficiency of plants.
All right, looks like we are running out of time.
I guess so. Thank you, everyone, for joining us for episode 3 of the Hyperthesis. And we will be back again next week for another episode.
On that note,
Yeehaw.
have a good day.
Bye, everyone.